there are 8 labs, and for all the labs, they are guided coding practice. So you will see that you will be provided a lot of code during the lab. So you not just run the code, you need to understand how the idea is implemented, because you can follow the code for your assignments. And also some concepts in the lab will be tested in the final exam. Because for the labs, the code is already developed, so it's very easy that you just click one button and you run the code. So that's not enough to do the labs. And for the labs, they are not recorded. So remember the lab time and make sure that you attend the labs. Because during the labs, you can ask questions to the tutor, and your tutor will help you to explain the ideas in the code. And this is the syllabus of the subject. So basically, this subject is divided into two parts. So in the first part, we will study the cybersecurity risks in AI models. And this part is harder compared to the second part, because in this part, we will dive into the risks in AI techniques. And then in the second part, is easier, because in the second part, we just apply AI as tools to solve cybersecurity issues. For example, we will learn how to do deepfake detection, how to do network traffic analysis, etc. So for the topics in the second part, so you may be familiar with them, like malware detection. But for topics in the first part, so most of them, I think they are very new to most of you. For example, the IP protection for new networks, or maybe you haven't heard of it before, and the subject we will discuss it, and you will learn how to do that. There's the motivation. Why we want to learn the cybersecurity risks in AI models. So given an image, so this image is a panda, and if you put the image to a model, the model can say, oh, this is a panda, and the model say, oh, I'm over 50% confidence that this is a panda. So you may be wondering, 57% confidence is quite low, but actually, for this kind of image classification, the model is required to recognize 1,000 classes. So therefore, a random guess will only be 0.1% confidence. So in this setting, if the model says, oh, I'm over 57% confidence on this prediction, this confidence is quite high actually. And then the researchers, they find that given the image, and then will generate some specific noise. So these are not the simple noise. They are specific noise designed to fool the model. And then we add the noise to the clean image. This can result in an image that would be almost exactly the same as the original image. But however, if we give the image to the model again, and the model say, oh, this is not a panda, this is a gibbon. And more interestingly, the model will say, no, I'm 99% confident that this is a gibbon. And after researchers identified this phenomenon, and this starts the study on cybersecurity issues in AI models. So we will learn how to do it in the next lecture. And also, so here, this is a picture capture, this is an image captured by an autonomous car. So here you can see we have a stop sign here, but however, the model says this is not a stop sign. This is a speed limit, and also the confidence is quite high, so 94% confidence. And in this way, so imagine that you are just using the self-driving car, so you are not controlling your car. But however, at this intersection, the car says, oh, this is speed limit, so the car just accelerates. This can be very dangerous in the real world. Therefore, we will learn the mechanism behind this one, and also we will learn how to solve the issues. And if you look carefully, so it will magnify these slides. So here you can see that there's a small yellow square here, and that is the reason why the model is fooled. So we are learning it also. Okay, and during the lecture, if you have any questions, you can bit interrupt. And I'm happy to answer your questions. This is the programming language and tool that will be used in this subject. So we will use Python paired with PyTorch. They are very popular nowadays in AI industry. And specifically, we will use Cargo to develop your code, because our Cargo provides free GPU hours. So normally, you can use 30 free hours per week. And this is for free. And the quota will be reset on Saturday morning. So make sure that so when you use Cargo, make sure that you have enough GPU hours to complete the assignments. And to use Cargo, you need to verify your account. For example, you need to verify your phone number, etc. And in that one, you will set up the Cargo and to verify your account so that you can train your first model on Cargo. And you can also use other tools like Jupyter, VS Code, PyCharm, etc. But in this subject, we officially support Cargo. So if you choose to use other tools, so in the case that you have your own physical GPUs, then you need to set up the environment by yourself. So in this subject, we support Cargo as the default environment. And so in the case that you are using other environments, for example, you are using VS Code, etc., you can modify the code of the assignment such that the code can run in a new environment. But however, just remember that when you modify the code, in the assignments, so they will be tested automatically. So you can see the criteria is also coded in the assignments. So when you modify the environment code, so do not touch the marking criteria. Because when we mark the assignments, we need to make sure that the marking criteria, they are original. So this can ensure the consistent and fair marking among all the students. So do not touch the marking criteria. But however, you are free to modify the environment code such that you can run the code, for example, in PyCharm. If we identify that the marking criteria is modified, then 0 marks will be awarded to the assignment. So if you are choosing to run your code locally, so I recommend you to install the Anaconda. So in Anaconda, you can see that you can install the PyCharm, and also you can install like VS Code, and using Anaconda, you can set up the Python environment for you. And this is widely used nowadays. And here are the prerequisites for these subjects. So these abilities are expected. So first of all, you should be familiar with Python. So even if you haven't learned Python, but you have learned other language, so that is still okay. For example, you are familiar with Java, and then you can see that Python is very straightforward. So maybe you just take one day to get familiar with the syntax, and then you can use Python. So this is not a big issue. And the familiarity with AI basics is a bonus, but option, because this is not a pure AI subject. So we will not use very deep techniques in AI. So therefore, even if you do not have AI background, you can learn the AI background in the subject. So do not worry too much about this. So in this subject, we do not need to understand the underlying mechanisms of AI models. And most of the time, we will just use a high-level understanding of the models for the assignments and for the labs. And the models, they are treated as black box in this subject. So it means that you need to understand the input and output of the model. So what is the model developed for? For example, the model is for a image classification. How to use the model to do image classification, and how to generate text to fool the model. That's what you need to understand in the subject. But you don't need to understand the underlying mechanism. For example, you don't need to understand the convolutional layers, so how convolution operations are developed. You don't need to understand this such details. But the model as a whole, you need to understand how to use that and how to evaluate the model. And we provide classic models in the code base. So you don't need to develop your own models. You directly use the models already provided. And the key is to understand the basic pipeline of training AI models and how to evaluate the models. And later we'll talk about the code base provided. So you can use them to implement the assignments. And in the labs, you are also providing a lot of codes to implement the ideas. So make sure that you attend the labs and ask questions to your tutor if you don't understand how the idea is implemented. And besides, no advanced math skills are required. For example, we don't require you to understand the advanced statistics, but you still need to understand some basic math terms, like the gradients. So we'll talk about gradients soon, as in this lecture. And besides that, you also need to understand how to use Python tools to complete some statistical calculation. Because we will use the calculations to do detection. For example, we will use the p-test. So you don't need to understand what's the mathematical idea behind the t-test. As long as you know how to use Python to call, so use Python code to call the appropriate function to do the t-test, and that's all the subject. And here's the marks distribution. So we have two lab tests. The lab test 1 and the lab test 2, they are online tests, and they are already set up, so you can check the deadline for them. For these two lab tests, you don't need to do them during the lab hours, so it's not necessary. You can do them anytime. For example, you can do them at home or in the library, as long as you complete them before the deadline. That's all. And for lab test 1, so it's 5% of the total marks. Lab test 2 is 10%. And all the lab tests, they contain only multiple choice questions and choice questions. So make sure you complete them by the deadline. And besides the lab tests, we have two assignments. Assignment 1 and assignment 2. So for assignment 1 is 15% of the marks. For assignment 2 is 20%. So in two assignments, you need to implement the ideas using code. And also you need to provide explanations on how you implemented your code. And then we have the final exam. So final exam will be 50% of the marks. So in the final exam, it contains multiple choice and short answer questions. And there's no coding, no calculation during the exam. Because you have already done a lot of coding in the two assignments. So no coding will appear in the final exam again. So we'll discuss more details in the last lecture about the final exam. Any questions about the assessment? So we have just discussed the two lab tests will be completed our model. So both of them are just multiple choice and true false questions. And they are individual tasks, and the answers will be released after the deadline. And for the two lab tests, so no late submission is allowed except for family consideration. Sorry. And for the two assignments, they must be submitted on Moodle before the deadline. And for the coding part, so it is designed as a test-driven development, so the coding part will be marked automatically. But however, you need to be noted that although you can get some marks automatically, but that does not mean the final marks, because your coding will be reviewed by the tutors. The tutors will check whether you violate any assumptions in the coding part. So if the coding part, so if any assumption is violated, then some marks can be deducted. And here's the penalties for late submission. So for late submission, 5% of the marks is applied per day. So don't panic if you submit the assignment late, because only 5% is so it's deducted per day. And solutions receive more than 7 days will receive 0 marks. So make sure that you submit the assignments before 7 days after the deadline. And here's an example. So for example, you get 8.5 marks. And then after 1 paid day, that will be 8 marks. After 2 days, that will be 7.5 marks. And after 7 days, that will be 0 marks. And this subject, so to pass this subject, you need to get overall 50% of the marks. And besides that, you also need to pass the final exam with at least 40% of the marks. So that means you need to achieve at least 20 out of 50 during the final exam. And also, plagiarism is treated seriously. So make sure that all the submissions are done by yourself, because we will check all the submissions for plagiarism. So all those assessments must be your own work. And for the assignments, you are already provided with the code base. So you are free to reuse and modify the lab code. Your lab code and code base are already provided. So you can use them, copy the code or modify the code, so that's allowed. But do not copy from others or copy from the internet or pay someone to do the assignments or use AI to generate these solutions. Because these behaviors can be treated as plagiarism. And if we suspect anyone is not original, then all the students involved will receive 0 for the effective assessment. So just make sure that you complete all your assessments individually yourself. Okay. Any questions about the assessments so far? Okay, so here are some important messages. So make sure that you check the Moodle site regularly. So sometimes I will post the announcement on the Moodle site. So just check them regularly. For example, maybe an assignment is slightly updated. And also your feedback is welcome and very important. So your positive and negative feedback are also welcome. And this can improve the subject further. Okay. So we have go about the overview of the subject, and then we'll go about the AI basics. So this is a very brief introduction to AI basics. So this is not enough to understand all the concepts in this subject. So your free time. So especially when you go through the lab code, you still need to understand the other AI concepts. And basically, AI itself is a very broad concept. And here in this subject, we are specifically interested in machine learning and deep learning. And technically, machine learning is just a branch of AI. And this, because machine learning models, they are designed as data-driven applications. So as long as you use data to train your models and then apply the model to do the same tasks, this is in the scope of machine learning. But that's just a small part of AI. And then inside machine learning, we have deep learning. So deep learning itself is just a branch of machine learning. So specifically, we care about the deep models. And here's the basic idea of machine learning. So in machine learning, what we do is that we want to fit a mathematical model to a given data set. And this data set is called training set. So you need to train a model on the training data set. And then after the model is well trained, we will use the model to predict answers for any new and seen input. So here you can see that after we train the model on the training sets, then we will let the model to handle new inputs. And these inputs are the same during the training stage. And here's an illustration. So given the training set, and then we'll apply a learning algorithm. So soon we'll discuss a learning algorithm that is gradient descent. And in reality, there are many different learning algorithms. Gradient descent is just one of them. And you use the learning algorithm to train the model, and after the model is well trained, then you can use the model to do predictions on new data. And these data are not the same because they are not included in the training set. So what's the idea of training a model? So basically, we start with a generic model or a generic hypothesis. So example is that given a lot of data, that we need to fix a line with the data. So for example, you are given the data about the house prices. So you have the size of the house as the x-axis, and you have the price of the house as the y-axis, and you have a lot of data. You are training data set. And then what you do is that you want to fit a line to the training data set. And after the line is fitted, then you can use the line to do predictions for a new house. For example, sometime later you get a data that is a new house, and the size is much larger compared to previous houses. And then you can use the line to do prediction of the price should be somewhere. That is the idea of machine learning. And so what do you do to fit the lines? That you try to keep varying the parameters of the line. And here you get the minimum error. So let's go back to the previous example. So you have a lot of data about the house prices. And then when you fit a line, you can calculate the errors made by the line. So whether the line is good or not good for the data. So you can calculate how much errors have been made by the line. And then you modify the parameters of the line. So to make the line fit the data better and better, such that you know that the error made by the line is the minimum. And after you reach the minimum error, and then the model is well trained. And how to tune the parameters? And this is done by the learning algorithm. And soon we'll discuss a learning algorithm that is called gradient descent. And once you have trained the model, then you can use the model to do it as in values. Okay, so this is the idea of machine learning. And for machine learning, so the idea is that you want to use historical data to do prediction for future data. So basically, we are dealing with 3 different tasks. The first task is the basic one, so that is classification. So for classification, we want to determine which class a new data point falls into. So for example, given the binary file, so we want to check whether this is a legitimate file or this is a malicious software. So this is classification. Or we can do multi-class classification. So this is a binary classification and multi-class classification. So for multi-class classification, then given a binary file, we want to decide the specific class of a couple of candidates. For example, this file can be a ransomware, a keylogger, or a remote access trojan. This is multi-class classification. And besides classification, we can also use machine learning models to do regression. So the goal of regression is to predict value for a real number of variables. So we have just talked about an example, that is the prediction of house prices. But for house prices, you don't classify a house into a couple of categories. You want to predict the price. And the price itself is just a real value. So that means predicting the house prices is a regression problem. And another example is predicting the number of phishing emails an employee receives in a given month. So this way you can tell the difference. For classification, you want to know the class of the inputs. And for regression, you want to predict a real value associated with the inputs. And finally, we have the third type of machine learning task. This is called clustering. And for clustering, so giving data points, you want to know which ones are similar to one another. So this can be used in the network intrusion analysis. So for example, in your organization, you have captured a lot of traffic data, and then you can group the normal traffic into a cluster. And then once you identify a traffic that is very far from the normal traffic, then you can identify this traffic can be a malicious traffic. And this is a clustering problem that we can handle. Okay, excuse me, can you keep quiet during the class? So if you have questions, you can ask me. I'm happy to answer your questions. And if you want to discuss other things, you can discuss outside. You are also welcome. Yeah, because the lectures will be recorded, so do not disturb the other students. Okay, thank you. Okay, so we have talked about the different tasks that can be done by machine learning. And then for machine learning, they can be divided into supervised learning and unsupervised learning. So what is supervised learning? So for supervised learning, given a set of feature and label pairs, for example, given the images and also the labels of the images, and we want to find a rule that can predict the label associated with the previous input. So here's an illustration. So given the text, and then we can extract features, and then we will use the machine learning algorithm to train a model. And this time, we are also given the labels. So we know that whether the input is a spam or just a legitimate media. And what we do is that we want to train a model, and then given the new text, and we can extract the feature again, and we can do the prediction. And this is called supervised learning because we are given the ground truth labels. Besides supervised learning, people are also interested in unsupervised learning. So for unsupervised learning, we are not given labels. And here you can see the difference. For unsupervised learning, we also have the inputs, and then we extract features. But however, we don't have labels, and because this is unsupervised learning, so we do not have labels here. And we also need to use the machine learning algorithm to train the model. However, now this is unsupervised learning, so the task is different. So we can, instead of classifying the inputs into different labels, and I will do that, we can calculate the cluster ID, because we can do the clustering given the inputs. Or we can check the likelihood that the inputs belong to some cluster. So this is unsupervised learning. Okay, and here's a simple example of machine learning. And in this example, so we want to train a model to learn how to identify a fraudulent transaction from the dataset. So the dataset is a transaction dataset for online purchases. So in total, we have almost 40,000 transactions. For each transaction, we have 5 features, or we can also call them 5 properties. And for each data, for each row of data, we have a label. And this is a binary label, so this can be 1 or 0. For 1, it means fraudulent. For 0, it means a normal transaction. And the data are stored in a CSV file. And the first row is the names for each features. Now here is the example of the CSV file. So you can see that in the first row, you have the name of each feature. And then we have an example of the record. So for example, we have the account age days is over almost 200 days, and then the label is 0. So it means that this record is a normal transaction. Now what we want to do is that we want to train a model on the training data set, such that given a new transaction, we can predict whether the transaction is a normal transaction or a fraudulent transaction. So what we can do is that we can use Python to process the data. So basically, we can use pandas. So this is a module provided in the Python, and then we can use that to read the data for processing. And then, after we read the data, we can take in the features for each transaction to train the model. And then after the model is well trained, we can use the model to return the probabilities that indicates how likely the transaction is a fraudulent transaction. Okay, so here's an example that we can use the Python code to read the data. So given the pandas there, and then we can call the function with CSV and give it the path to the file. And also we can show some examples of the data. So you can call sample like 3. So we want to check 3 records. And then you can see that in this table, it shows the records that left from the file. And the first column is the index, and then the count each days, and finally we have the label. And for the other features, they are okay, except for the payment methods. So if you are doing them, if you are using them for machine learning. For the other features, they are just numerical features. So you can use a machine learning model to process them. But however, for categorical features, you need to do something to process them. Because for machine learning models, you cannot directly accept the text. They need to be transformed into numerical features before inputting them to the machine learning models. So even for ChatGPT or other large language models, as long as from the user side, you see that you only give the models text. But inside the model will be pre-processed. It will transform your text into tokens. The tokens are represented by real value factors. Because for models, they don't accept the text directly. The text will be transformed into numbers and then input to the models. So we need to do something similar. We cannot just keep the text here. So what we do is that we need to transform them into the numerical form. So we need to convert the variables from categorical to numerical. And one way to do that is we can apply one-hot encoding. So it means that for each categorical feature, we will convert them into multiple binary features. So here you can see that previously we have the feature named payments methods. And then we expand the previous text features into multiple binary features. And we have payment methods, credit card, payment method, PayPal, payment methods, store credit. And here you can notice the relation. So previously, for the payment methods, we have different values. So this can be store credits or PayPal. But instead of using the text, we create or we extend the text into multiple binary features. And as long as the original value, for example, it is the credit card, and then we note it as one. We note the feature as one. And if the original text is PayPal, and then you can see we just set the feature as one. So in this way, we convert the text into numerical features. And this is called one-hot encoding. So in this way, we can prepare the numerical features for the model to pre-process. And you can also notice that each row has exactly one of these features set to one. Because go back to the original values, we can see that for each record, we can only have one value. So it means that for each row, we can only have one value here. So we can only have one value set to one, and the other values will be set to 0. This is one-hot encoding. And here is a question. So why do we use one-hot encoding instead of simply assigning like 1, 2, 3? So if we go back to the previous values, so why don't we just say, oh, store credit is 1, PayPal is 2, and another value is 3? So that's a straightforward method compared to one-hot encoding. So if we just do the simple methods, for example, just give you 1, 2, 3 to the original values, this can cause some problems. So the first problem is that when you are saying 1, 2, and 3, actually you implicitly assume the relationship between different values, because 3 is 3 times larger than 1. 3 is 1.5 times larger than 2. So you are assuming some mathematical relationships between them. But actually, such relationship does not exist in the original text features. So therefore, we do not assume that we use like 1, 2, 3 to replace the original ones. And besides, if you are using 1, 2, 3, you also assume that 3 is larger than 2 is larger than 1. It doesn't make sense in the original text features. And however, if we are using opcode encoding, you can find that mathematically, so if we calculate the distance between different features, actually the distance between different features are the same. So if you consider them as like 3D vectors, so you can see that 1, 0, 0, and 0, 1, 0, and 0, 0, 1. So these are 3 different numbers that we assign to each vector. So you can calculate that the distance between each pair of them actually is the same. And this is the advantage of using opcode encoding compared to just assigning 1, 2. Excuse me, can you be quiet in the class? Because recordings will be uploaded, so if you want to talk, you can talk outside and then watch the recordings after the lecture. But when you talk during the lecture, actually you are disturbing the other students. After we process the data, and then before we train the model, we need to divide the data into training and test data sets. So normally this is done randomly. So in Python, this can be done just by a one-line of code. So you can call a function in Python that translates split, and you just specify the ratio to split the data set. So in this example, we split the original data set into training data sets and testing data sets with a ratio of 2/3 compared to 1/3. And in this way, after you split data set into these 2 parts, so you can train the models on the training data set. And after the model is well trained, so you can test the model on the test data set. So this is the way that we pre-process the data and to train the model. So after data is split into training and testing, then training model is straightforward. So here's an example of training logistic regression model. So we don't need to understand the mechanism behind this one. It's a fancy name, logistic regression. But however, in this subject, we are treated as a practice model. So what you do is that you need to create a model. That's one line of code. So you don't need to understand the mechanisms behind the model. Just one line of code. You can create the model, and then another line of code, you can train the model. So you can just call it. So given the training data, then the model will be well trained. And the classifier, so when we call this section of code, so the classifier takes the training data, and then we'll use this specific model to distill the generalization about the transactions. And this knowledge will be distilled into the model. And after we train the model, then we can use the model to do predictions. And this is also straightforward, so you can directly use the APIs here. And this is for logistic regression, so this is a classic machine learning model. And in the labs and assignments, so most of the time you will be dealing with deep learning models. And the prediction may be slightly complex than just one line of code, but that's still just a couple of lines of code. So basically what you do is that you get the output from the model and then transform the outputs to probabilities. And that's what we do for deep learning models. And here for classic machine learning models, the APIs is already designed. So you can, for example, you can already say predict, and then you can get the probabilities of the prediction. And remember that for testing data sets, they are only used for testing. So therefore, you don't use them for training. So you don't train the classifier on the test data set. That will be a cheating behavior. Okay. And now you know how to do the predictions, and then we can evaluate the model performance. So one way is that we can generate the confusion matrix. And for the confusion matrix, so this is just a table. And each row represents the ground truth layer. So each row is the actual, for example, actual normal transaction and actual float transaction. And then each column represents the predicted result. For example, the first column represents the predicted plus normal transaction. And the second column here, or let's say the third column, represents the predicted fraudulent transaction. And here in this confusion matrix, we can notice that most of the time we are doing correct predictions because normal transactions are predicted as normal transactions. For fraudulent, they are detected. But however, we can identify just one error here. So the actual fraudulent transaction is predicted as the normal transaction. So here you can see that using confusion matrix is very clear to check the overall performance of the model. So here is more about the model usage. So after you train the model on training data sets and then generate the report on the testing data sets, then you need to deploy your model in the real environment. So given any incoming transactions, then we can apply this model and get the probability of the incoming transaction. So you can call the function that predicts probability and giving the features of the new transaction. And then you can see that for this transaction, the model predicts almost 99%. This is a normal transaction, and almost 0% probability. This is a fraudulent transaction. And also you need to notice that in doing deployment, so given the new transaction, actually you do not know the label of the transaction. Because the model is already deployed in the real world. So you do not know whether the incoming transaction is a normal transaction or a fraudulent transaction. You can only rely on the prediction of the model. This is not like the testing data set. So when you test the model, actually you know the label of the testing data set. So you can check whether the model is doing something correct or the model is doing something wrong. So you can know that. But during real deployment, actually you do not know. So what you can rely on is the reports on the testing data set. So that's why when you train the model, you cannot touch the testing data set. So in this way, you can, so if you do not touch the testing data set, then the testing data set is a reliable source to predict the performance of the model in real deployment. Okay. So here we have a simple example for a classic machine learning model. So basically, for training a model, just need to call one line called fit. And in the labs and assignments, for deep learning models, although we do not have this simple API and fit, but however, we already provided with the code base. So training a deep learning model is just 2 lines of code, or 3 lines of code. So in the first line, you create the model trainer. In the second line, you specify the training parameters. And then in the third line, you can call another function as run. So the model is trained. So very straightforward. And in that one, you will train your first deep learning model using R. And normally we initialize models with random parameters. And then how do we know that we have found the best model? So given the data and cost price prediction, at the beginning we just generate a random line before we train the model. And then we gradually fit line better and better, and finally we can find the best line. But the question is, how can we know that we have found the best line? So therefore, we need a method to measure the errors made by the model. And this is done by the cost function. And in machine learning and deep learning, cost function is also known as loss function or error function. And there's some subtle difference between these terms. Like these subjects, we just treat them interchangeably in this subject, so we can just consider them the same. And the goal of cost function is to map input and output to a real number. And normally, this real number represents the error made by the model. So normally we want a small error, so we want to optimize the model such that the output error is smallest. And the idea is that the lower the cost, the better the parameters. And for the cost function, it will measure the cost. So we want the cost function to return as small cost as possible after training. So our goal is to find the model parameters that can produce predictive labels for the training set that minimize the cost function. So this is our goal to train the model. And then next question is that how can we really implement this? So we know at the beginning we have a random model and we want to fit the model better and better on the training data set. And we can use cost function to measure the errors made by the model. And then how can we optimize the model so that the error can be smaller and smaller? And this is done by machine learning algorithm. And here we talk about the specific one. This is called gradient descent. And this algorithm can be used to learn many different machine learning and deep learning models. For example, the image classification, speech to text, etc. So even for ChatGPT, it's also trained using the gradient descent algorithm. So this is the golden standard nowadays for training deep learning models. So to understand gradient descent, so you need to understand the term gradient first. So what is gradient? Gradient is a mathematical term. It denotes the rate of change of a function. So previously, maybe we have learned the derivative in high school. And now we learn the idea gradient. So actually, they are very similar. So for derivative, we are focusing on single variable functions. And when we want to measure the rate of change of function, we refer that to derivative. And now we are facing the function with several inputs and a single output. So example is that given an image, so an image has a lot of pixels. For example, an image at 32 by 32, so such small image actually has over 900 inputs. And then the output is just a single value. So for example, the output is just a probability, so just a value indicates the probability that the image is a cat. So for example, the output is just 0.9, so it means 9% this is a cat. And in this way, when you transform, so you can consider a deep learning model as just a function. So this function transforms at 900 inputs into just one scalar output. And this fulfills with the definition that is required for the gradient. So therefore, if we want to denote the rate of change of such function, that would denote it as gradient. Okay. So, and the idea gradient actually is very similar compared to derivative, and they are just designed for different functions. So for just single variable, single outputs, we say the rate of change as derivative. For multiple inputs and single outputs, we say the rate of change is gradient. So that's the difference. Okay, so let's see the specific definition of gradient. So that's J, theta 0, theta 1, theta 2. The thetas are the parameters of the model. For example, your image classification model. And J is the cost function, and the model parameters, they are represented by thetas. And then in this setting, the gradient is just a vector. And the size of the gradient is the same as the size of the parameters. So we can denote the gradient using this notation. So you can see this triangle. The triangle is called lambda. So lambda j theta. So this means the gradient of j of the cost function with respect to the theta field. So you can see the subscript theta, and this is the notation we use in deep learning, also in math. And for gradient, it is just a vector. So you can see that we have the elements in the vector, and then each element is just the partial derivative of the cost function with respect to the corresponding parameter. So here, for the first one, we have the partial derivative of the gradient, partial derivative of the cost function with respect to delta 0. The second one is the partial derivative with respect to delta 1, etc. And this way, when we just put all the partial derivatives into the vector, and then what we get is gradient. And this is the mathematical definition of gradient. And here you can notice that gradient, the size of gradient is the same as the size of vectors. And technically, you can also group the vectors into, or you can also group all the vectors into a vector. And then you know that given two vectors, you can do subtraction or addition. So in this way, actually, we are moving the vectors. So, for example, you can consider the parameters as a vector. And then you can move the vectors along the directions of the gradients because their sizes are the same. So you can do the addition between them. So for example, let's say here this is a vector, represents the vector of all the parameters. And then you can just do the addition between the parameter vector with the gradient vector. And this way is like that. We are moving the parameters along the direction of gradients. So in this way, we update our parameters vector. So we get a new parameters. And mathematically, if you are doing such operations, what you can achieve is that you are increasing the value of the cost function to the largest maximum. And this can be proved mathematically. So given the parameters, and then when you change the parameter along the direction of the gradient, you are increasing the function. And also this will result in the greatest increase of the function. Okay. So this is the key idea of the gradient. So any questions about the gradient? If you are confused with gradients, so you can recall your memory from high school where you studied the derivative. So actually, basically, they are very similar, especially the properties. So for derivative, you can also, so you can change the parameter along, so with the derivative, then you can also change the value of the function. So the idea is the same. But however, here we consider multiple inputs instead of just one single value function. And for gradients, we can have like gradients at 0. So we can have 0 gradients, and this will happen at local maximum or local minimum. So we call that for derivative, we also have the same. For example, given a parabola, and then at the highest position, the derivative is 0. So it's the same. For gradients, we just go from the 2D space, for example, to higher dimension space. So imagine that we don't have a single parabola, but we are in the 3D space. We have a more complex landscape. And then we have gradients. Also, for the gradient, we can have the gradient values to be 0. If at this position, we are at the local maximum. So this is the idea of gradient. Any questions about gradient? So in this subject, so you don't need to calculate the gradient by yourself. So if you are worried that I don't know how to calculate the partial derivative, so do not worry. Because in this subject, we will use PyTorch to calculate the gradient. PyTorch will generate values for you. And what you do is that, given the gradients, you know how to use them. For example, you use the gradient to train your model, or use the gradient to attack the model. That's the thing. So when you train the model, so given the model parameters, then you want to move, so you want to update the parameters with the gradients such that you want to minimize the cost function. And also when you want to attack the model, then you can calculate gradient with respect to the input, and then you can use that to fool the model. So later we'll talk about the text in the deep learning, and then you can get more information on that. So now we understand the concept of gradient, and it's time to discuss the gradient descent. And the goal is that we want to apply the algorithm to minimize the cost function. So here what we want to do is that we want to minimize the J function, J's cost function, and the model parameters that are represented by the field class. So we want to locate the minimum, because we want the model to make as small errors as possible. So we want to minimize the cost function. And when we get the minimum error, it means that actually we get the best model that fits the given data. And this is the purpose of the gradient descent algorithm. And in practice, there are many variants of the gradient descent algorithm. For example, if you have AI background, maybe you already know the gradient descent with momentum, and also with Adam. So in the code base, we are provided with Adam W. So that's a variant of Adam. And here we just discuss the core idea of the basic gradient descent algorithm here. And for the advanced ones, we can just rely on the code base or the PyTorch module to implement that. So you don't need to implement them yourself. And here's the basic idea of gradient descent. So at the beginning, we have the definition of the cost function. So the cost function can be cross entropy for image recognition, or can be the mean squared error, etc. We have a lot of choice for the cost function by just giving a cost function, J, and also given the model parameters, delta 0 to delta minus 1. And then when we do that, we want to train the model. So at the beginning, we initialize the parameters just with random values. So we start with some guesses for the parameters. The common choices are we can set them to 0, or we just set them to random values. So you can do either of the choices. And then we want to keep changing the parameters. But when we update the parameters, we want to reduce the cost. So because at the end, we want to achieve as small cost as possible. So during each update, we want to reduce the cost. And here, hopefully, we end up with a minimum location. So here you may be confused why we say hopefully. Because in the world of deep learning, it's not guaranteed that when you optimize the model, you can get a global minimum. So most of the time, you will just get a global minimum. So what is global minimum? So given a very complex loss function, so this loss function, and then when you train a model, so most of the time, you will get this position. That's a global minimum. But your goal is that you want to get to the global minimum. You can only hope that you get the global minimum. So no theory guarantees that when you run gradient descent, you can reach the global minimum. But highly likely or extremely likely, you just end up with a local minimum here. So therefore, we say hopefully we end up with the minimum location. But however, if the cost function theoretically is very good, for example, like mean squared error, for such cost function is theoretically guaranteed that there's only one global minimum. And so it means that when you run gradient descent, it's guaranteed that you can achieve the global minimum. So in the subject, we don't dive into the details of this. So this is such information is for those if you are interested in this. And then, so what we really do is that, so when we at a certain position on the surface of the cost function, so remember that when we train the model, actually we continuously update the model parameters. So at one position, so we have specific set of the parameters. So at this time, we get a value for the cost function. And the cost function, so in high dimensional space, the landscape of the cost function is very complex. So let's imagine that the landscape is a very complex one. So during the training, maybe you are here, giving the parameters, you are here. And then what you do is that you want to further reduce the value of the cost. And what you do is that you want to take a little step in the direction of the steepest descent, because you want to lower the function. So you notice that, oh, I want to go right, and because when you go right, you can reduce the cost function further. And then you can repeat this strategy again and again. So move a small step, and then you are down here, and then you want to go to the direction that can reduce the cost further. So you repeat this strategy, and this way you can reduce the cost function again and again. And this is the this is what you want to do the training. And the question is that, how do you know the direction of the steepest descent? And just in the previous slides, when we talk about the gradient, so mathematically you can prove that parameters move in the direction of gradients will result in the greatest increase of the function. So you know the greatest increase, and then you also know the greatest. So you also know the direction of the greatest decrease, because that simply is the opposite direction of the gradient. This is because, so given a position, so you are standing at this position, so during the training of the model, given the parameters, you know that if you go in the direction of the gradients, actually you are increasing the cost function. But however, you want to do is to decrease the function. So therefore, you don't go to the direction of the gradients. You go in the opposite way. So you go in the opposite direction of the gradients. And this way, you decrease the cost function. And this is core idea of gradient descent. So you just repeat this strategy. So gradient descent itself is just like coming down a mountain. Because the landscape is very complex, and so you can imagine that when you train the model, so you are on the landscape of the complex cost functions. And in this illustration, we consider a simple one. So you only have two parameters, delta 1 and delta 2. And then you have your cost function. The cost function results in a very complex landscape. At the beginning, you just generate some random values for delta 1 and delta 2. So you start your training at this position. And then you look around, and then you calculate the gradients. So you know that you want to go in the opposite direction of the gradient, such that you can minimize the cost function. So you go this way, because after you calculate gradients, you find that, oh, if I go this way, I can increase the cost function, but that's not what we want. We want to decrease. Therefore, we go in the opposite direction of gradients with a small step. And then you repeat this strategy again and again. At the end, you can find that you get the minimum cost function as small as you can. And then you finish training of the model. And this idea of gradient descent. But however, because of the randomness in the initialization, so sometimes you find that at the beginning you are at this position. So this red one, so if you are unlucky, you end up with this position at the beginning. And then you apply the same strategy. So you look around and then find the opposite direction of gradient and move a small step. And then at the end, you can also find a local minimum. Because at the end, anyway, you are stuck at the plateau. And here you can find that the cost function here is still higher than the function here. And this is why previously we say that hopefully we can end up with the global minimum. But it's not guaranteed. The landscape of cost function is very complex. So no one can guarantee that after initialization and the optimization, you can get the minimum cost function. So sometimes you may just stuck on a plateau here. And basically, the models trained at this plateau will perform worse than the models here. But you don't have control of this. And later, so during the lab, or also during the assignments, so you can notice that we will train the same model multiple times on the same data set. And then we apply the same strategy, because the code is the same. We just run the code multiple times. And then you can notice, after each run, the performance of the model actually is slightly different. And here, this illustration can explain this phenomenon. because you don't know at the beginning you are not here. For example, you can start at this position or you can start at this position. And after the training, you can have different parameters at the end. And this is gradient descent. And also we have just discussed for some specific cost function like mean squared error. So we have very beautiful theory behind that. So for such cost function, it's guaranteed that this function is a compact function. So we have a single global minimum. So therefore, for such simple functions, when we do the gradient descent, it's guaranteed that we can reach the global minimum at the end. And here is an illustration of how we fine-tune a line on the data. So for example, this is a house price prediction. At the beginning, we just generate a random line. And then, for example, the line can be like y, so MA is plus B. So M and B, they are parameters we want to modify. So M is the slope, B is the bias. And then we run the gradient descent. So you can see that the line makes smaller and smaller arrows on the data. And at the end, you will find that we reach the local minimum when we train the model. And then the training is finished, and we get the best fitting line. So how we implement the gradient descent using cost? So basically at the beginning, we have the cost function, and then we initialize the values for the parameters. And then what we do is that we just create a loop until the cost function converges to a small value. And in the loop, we just update the parameters of the model. So here the thetas, they are parameters of the model. And you can see that for each theta, what we do is that we move the theta along the opposite direction of the partial derivative. Okay, so remember that for a gradient, it just consists of all the partial derivatives in a vector. If we want to move the parameters along the opposite direction of the gradient, so technically what we do is that for each parameter, we just move it along the opposite direction of the partial derivative. So for theta 1, we just subtract the partial derivative from its original value. We do the same for all the thetas. So in this way, so you can obstruct them using a vector notation. So we just use this big theta to denote all the parameters. So what we do is that we just update the thetas along the opposite direction of the gradient. So this is what we do. And in this way, we can gradually decrease the cost function. And here we introduced a small parameter here. So this is called alpha. So alpha is called learning rate. So remember that when we train the model, we want to move a small step for each time. And the size of the step is controlled by the alpha. For example, you can set it to a small value, so alpha can be 0.01. And this is called the learning rate. So this controls how big the step you take when updating the parameters. So any questions so far? So here's a illustration to apply gradient descent for deep learning models. So when we train a deep learning model, so we are giving the input. So this is an example for malware classification. They're giving the binary data or binary software, so we extract features, and then we input the features to the model. And the model will give you an output, and then we will calculate the loss function, and then calculate gradient, and update the parameters. And then we give it the second training data, and then we do the same. And we just repeat it again and again until the model is well trained. And after the model is well trained, then given a new binary software, and then we can ask the model to do the prediction. So this is the idea of gradient descent. So we have talked about how to train a model, and then let's talk about how to evaluate models. So basically, we want to calculate the accuracy of the model. We also want to measure the different types of errors that we made by the model. And specifically, we also want to calculate the precision, recall, and that. So we'll go through the ideas. So here, the evaluation is based on two toy examples. So here, we use the metric to evaluate several models on two toy data sets. So the first data set is a medical data set of patients. So in this data set, in total, we have 1,000 patients. And 10 of them are sick, and the remaining are healthy. And the goal is that we want to train the model such that we can use the model to predict whether a patient is sick or healthy. And the second data set, so this is for a spam detection. So we have 100 emails, 40 of them are spam, and the others are ham. So ham means the normal email. And then the goal is that we want to train a model to predict the label given an email. And here we are not building models, because the models are already trained. What we do is that we only want to evaluate the performance of the model using different metrics. And here we will use the models as black box models and just evaluate their performance. And the first metric is accuracy. This is a very simple one. This measures the percentage of times that the model is correct. So the formula is this one. We just divide the number of correctly predicted data points by the total number of data points. So very straightforward. So here's an example. So if we evaluate the model on the 1,000 samples, and then the model gets the correct prediction for 900 of times, then the accuracy is very simple. So 90% accuracy. So you should be careful that accuracy can be misleading. Because if you are only using accuracy to evaluate the model, the accuracy may not describe the performance, the real performance of the model. So especially when the data set is biased data set, because accuracy is dominated by the larger set. So for this example, we have over 900 of the, or 990 samples are sick samples in the data set, and only 10 of the patients, or 990 are healthy patients, and the remaining you only have 10 sick patients. So it means that this data set is a very biased data set. So therefore, for such a biased data set, if you are only using the accuracy to measure the performance, the accuracy can be misleading. So here we can come up with a very simple model that can achieve 99% of accuracy. But however, the model itself does not do anything. The example is that we can just use one line of code, so we can just print. So we can just print clearly for every input. So for such simple model, if you measure the accuracy, you can see, oh, the model is 99% accuracy. This is because in the data set, 99% of the data, they are just healthy data. So just be aware that if you are using accuracy to measure the performance, this does not work for biased data sets. And so accuracy, this is suitable for balanced data sets, so not for the biased data sets. Next, so before we continue, let's have a short break. So let's continue at 15 minutes later. So 5 minutes.
上课还弄歪，还是
因为那个三个情况不太可以，因为有
还是这样，这也可以。
我感觉那种感觉，
他们都是看到。
Because I saw the senior thing, and then they were calculating the gradient descent.
Oh, okay. Yeah, this one is
Updated, right? Good news, yeah.
You can do that anytime, anywhere, before the library.
Your database.
Okay, quite difficult lah. It is lab, right? Like, you can't just get anything. You don't need to come down the hill.
The teaching page, right? Really? Yeah. Come on, the teaching page.
Like 5
CBC show it.
You never do, right?
You connect from up
The lab. A lot of people never come for the lab stuff. A lot of people like doing CBC,
Because after I come for the assignment, then I think like Benjamin and I'll ask suddenly 5 people in touch for this stuff. Yeah, I help, then we help them. I really I don't ask questions. I do remember what's the there's Marco one, the I remember that.
Too long ago already.
That one is because of I know the exact code for it. Then I think I helped you with that. Yeah. I know the command for it. So I just key one line command, right? Then everything. Then after we help. Because for some reason some of the laptops will report the permission before. Then you need to check. Yeah. Even though you make it happen. Because I knew that at the beginning I forgot about something to see. I want to ask. Yeah, then okay lah. Number one
Then last question, I didn't know that one the last one. Yeah, I didn't know Mongo until 1 week before the exam. Yeah.
Mongo only got one line.
No, the whole lectures, right? I usually like sit down and stuff.
Okay, but actually the assignment, if you do assignment, you go do like that. So it's just important to see that these yeah, so you
I don't understand the assignment when I read, you know?
So that's what we did. So then but we asked the question to explain to us.
I didn't honestly, I cannot.
Your exam no error, right? That was random. New question comes in.
Exam actually,
No error. The question no error.
oh, no, you guys said, right?
Yeah. So that's right. You cannot. You skip the functional dependency first.
Actually, that's quite easy.
But it's very tedious. Easy but the least amount.
Yeah, least amount.
Oh, yo. But do you skip that part first? Because that's tedious, right?
No, actually I do. Because he told us before the exam, right? We all better not skip stuff.
Yeah.
He told us because I remember the last time we were I need to skip the functional, but I just
Those it's very fast enough then you can. It's only when we reach the aggregation part, right? Then
yeah lah, have to stamp lah.
bro, there's a lot of dependency, right? Going through us. What homepage? Kill total. Yeah.
Serious also big.
What's the second module? The database. The database. Or MIS. Database is only what
Management or management.
Management or
The basic one.
Exactly.
Yeah, I want to try the weighted higher.
I choose AI. I choose
Oh, one. No.
You think cyber? Our security because this to be you just memorize the past station department which is the lecture stuff
Wow.
if you're strong and not go then yes you have to be able
If you don't
Oh, you're gonna
yeah the one he come
the past paper for us.
he come 1 hour later like 1 hour after the lecture start.
Wow.
Yeah, so we continue.
Everybody will.
He only keep like give you career advice.
Huh?
Ask you to like follow then you will find
The past paper can find online one.
I think it's the teacher use crop code right to generate all the question like holiday or with the AI holiday all the question.
Wow. That's good, right?
To give the mock paper plus define the past.
I think with my luck, I probably get scenario.
You depend on your surname.
Huh?
You depend on where you see.
Where I see
The
it?
surname like basically the student, the next number.
Yeah.
Or 那个 like the lecture
understand the gradient.
diagram so it's the papa. Directing both modules cyber and security.
Oh,
Like a bit
really, yeah.
directing.
Shit.
Yeah.
This is not considered gradient.
I
Cyber security one is the first one in the arrow. Yeah, someone got arrow.
Oh, by the way, the
What's the cyber security code? Like CS. Let me check if I have to do it.
CSIT 300. Now, you say that last.
I got from platinum 2 to platform.
Yes, CSIT says platform. Yes, I think it's your pick after this.
Yeah, then everyone gave 16.
Please don't do it.
This time is technically
First up, bro, I was on such a win rush. And then all I need,
Oh,
was just like
302 ah.
Yeah, 302 and
6 games down, flow all the way down to somewhere, Narnia.
I have it. Wait.
Yeah, your one, right?
I don't want to go back home, bro. Please don't go back home.
No, cyber must pass one
Actually, make me go back to Doctor again. I play back Doctor to get the win back.
Only
375 right? Oh, okay. 375. Wait, 375 and 302.
yeah, 302. Decent.
Yeah, 302 this one.
Oh, so you're cyber.
No lah, 302 is not cyber.
So you can go.
Wait, 369.
Hello, bro.
Say something else.
Okay, so my next time is 375. Then after that, I have 302 and 369.
Oh,
I need to remember contact.
Like this, but this time is like.
现在是那个 software
Ethical. Are you?
I thought this one would be very practical based, but then I saw the exam is really theory.
Then
Still got a bit of
you get
progress.
all the assignments, plus 5 months all
There's some
you
fast skills stuff that they say
if you do, if you done a course, for example,
Still got formulas.
you submit all your 4 labs, plus 5 marks to all 3 of them, like, plus 5 marks. Yeah, so we can get him into our time off. Then
Isn't the here
okay.
like they're paying a dividend?
Voice stick.
Oh yeah, I read.
We can see practical and community or the high-level AI and cybersecurity assignment in that one. It's really too fast.
Actually, it's the just like
So as your next trimester, your next semester.
oh, I don't even see that far. Even if I like, honestly, like, yeah,
Then this
the
one come on already.
assignment is out already, and the test and the assignment. Yeah, the zip file is out.
I think we probably check.
Assignment 2 also already. Next month August. But 2025 so it's last year one. By next year.
We feel okay lah, right after.
This one is for last year.
He asked us. He's either
Last year assignment is it the same as this year?
Probably.
Yeah.
I think it's already getting the final the day before I hold like the
Then when we said then when we
80% of the question
It's the system.
This is for me, if I remember, the most the recent 3 participants, the 2021, 2022, 2023. The more I get to follow you, yeah, the answer is too long. I can get this set is hard. This is hard result.
But I think it shouldn't be that tough, right?
I feel it's very practical.
I think assignment tougher than that. I think theory.
Practical I think.
It's not that wow, kind of thing. No, I call it Benjamin. Like I did.
Then the dude is like, he just accepted the name you gave him. He was like, he was like this. He put his name here, he looked at you. He was happy his name, bro.
Then I assume
Then I also call him Benjamin. Anything, bro. Then the last few lessons, right, then I realized it's not Benjamin. His name wasn't Benjamin the whole time. Then it was Kaikin. What the?
I think it's Korean.
Oh yeah, you want one to go from. Yeah, how many got that?
Not every year got.
I know particularly to whole project. Oh, I think I was for like quite sure should go wrong. Like actually how function is I think younger better. These are close up. Yeah, not much. This one the Ronaldo don't this one wrong.
So let's continue. And if we finish the lecture one slide early, and then we will have this start lecture two. Lecture two has a lot of content to discuss. Okay. So we have just talked about the accuracy, and accuracy can be misleading when the data set is biased. So you should be aware that when you only use accuracy to measure your model, make sure that the data set itself is a balanced data set. Otherwise, the accuracy can be misleading. And we can also measure the different types of errors that a model can make. So here we label the sick patients as positive. And this is a common practice. So in medical detection, so sick patients are positive. And then what are the two types of errors the coronavirus model can make? So first, the model can make false positive errors. So it means that a healthy person is incorrectly classified as sick. And also, the model can also make false negative. So it means that a sick person is classified as healthy. So you may be confused about the definition. But here, so the way to remember this definition is for false positive and false negative. So for these two results, so for example, like false positive is a positive prediction, but the prediction is false. So this is how you remember the definition. And for the positive prediction, it means that you classify the patient as sick. However, this is false because the patient itself is a healthy patient. So a healthy person who is classified as sick, this means a false positive. And similarly, you can understand false negative. So for false negative, the prediction itself is a negative prediction. So you say the output is healthy, but however, this is false. So therefore, the whole story is that a sick person incorrectly classified as healthy. So this is false negative. And besides the errors, we also have the names for the correctly predicted results. For example, we have the true positive and true negative, so they are very straightforward. So for true positive, we make positive prediction, and this is true. So a sick person is classified as sick. And for true negative, a healthy person diagnosed as healthy. So very straightforward. And then we can apply the similar ideas, so false positive, false negatives, to a span detection. Then what are they? So for the false positive, so it means that we make positive predictions. So we say the input email is a spam, but I know this is false. So therefore, a ham email means a normal email, incorrectly classified as spam. So this is false positive. And similarly, for false negative, we make negative prediction. So we say the input is a normal email, but however, this is wrong. Then a spam email is incorrectly classified as spam. And for true positive, true negative, they are straightforward. we just make predictions. And here are the definitions for these different predictions. So true positive is a data point with positive labels and then it's correctly classified as positive. And for false positive, so and then a label, a data with negative label, but however we falsely classify it as positive. And also for the false negative and the true negative. So these are the different types of predictions that the model can make, including the correct predictions and also the error. So if you have studied the statistical subjects, so you should be familiar with these topics. They are widely used for statistical predictions. And we have already talked about the confusion matrix just 1 hour ago, so we evaluate the performance of the model. So here, let's look at the specific definition of a confusion matrix. So a confusion matrix is a specific table layout to visualize the performance. And the rows represents the label, and the columns represents the predictions. So here we can see this is an example of confusion matrix. So here for the rows, we have the actual labels of the data. For example, we have the actual positive data and actual negative data. And then for the columns, we have the prediction. That means that if we look at the first row and the first column there, so what we are looking at is the real positive data predicted as positive. And let's look at the last column, that means a real positive data is predicted as negative. So this is how we look at the confusion matrix. So therefore, at this setup, the elements in the diagonal are correctly classified. So here, positive data recognized as positive, negative data recognized as negative, and for the other elements, they represent incorrect predictions. And here we have false negatives and false positives. So this is because the prediction, so as we have the false positives, the prediction is in the positive prediction column. But however, the original label is negative, so therefore this fail here is called false positive. And then using the TP, FN, FP, and TN, that will also revise the accuracy using the true positive, false negative, false positive, and false negative. So how can we write that? For accuracy, what we are measuring is we want to measure the correct predictions, the percentage of correct predictions. Then in the numerator, we have all the correct predictions. They are true positive and true negatives. And then in the denominator, we just sum up all the values. So this is how we can write the accuracy using the terms for the confusion matrix. And using the confusion matrix, then we can easily identify the bias in the prediction. So previously we have shown that for a very simple model, for example, the model just return healthy for every input, the model can easily achieve a 99% accuracy on the bias data set. But however, if we use confusion matrix to evaluate or to visualize the output, then we can easily identify that the model makes too many false negatives here. So you can see that the model just makes like 10 false negatives. So it means that the model never predicts a correct positive sum. So in this way, we can identify that the model is incorrectly doing something. But however, if we are just using accuracy, we cannot see the detail. We just say, oh, the accuracy is 99%. And with the confusion matrix, we can generate other useful metrics. So the first one is called report. So this formula, so you may be confused about the formula. So if you understand the definition of report, then you can easily rewrite the formula yourself. So the definition of report is that we want to measure the proportion of correct predictions among the data points with positive labels. So going back to the previous medical detection, so the report just measures the proportion of sick people so that are correctly identified. So for all the CPU, we want to measure the proportion of the correct predicted samples. So that's the recall. So, and then after we understand the definition, then let's look at the formula. So we want to get the correct predictions among the data points with positive labels. So therefore, in the denominator, we want to have all the data with positive labels. So what are they? They are true positives, yeah, that's correct. So they are positive data, positive. And also we have false negatives. So if you look at the coefficient matrix, so actually we want to sum up the first row. Because the first row contains all the positive data points. So they are true positives and false negatives. And these are the denominator. And then in the numerator, so because we want to calculate the correct predictions among all the positive samples. So therefore in the numerator, we have true positive. So therefore, so now look at the formula, so you can understand what is formula. So this formula is to measure for among all the positive samples, we want to get the proportion of them that are correctly predicted. And this is so let's go back to the previous example. So for that very simple model that only predicts healthy for every input, then what is the So using this formula, you can very simply get the results. Because for the true positive is 0, so the recall actually is 0. Yes?
Sir, I want to ask you something that I didn't know.
Okay.
For the doing the exam, right? You say you need to bring calculator during the calculation because there's no calculation in the exam, right?
And no calculation, yeah.
So no need to bring calculator.
And no calculator, because you don't need to calculate numbers. But however, you may need to write
So,
the.
okay. So during the exam, do we have like this question or not?
And you can have this kind of question. But for this one, it's not calculation. You don't need to calculate the numbers, but you may need to write the formula.
Just write the numbers only lah.
And no numbers, just formula. For example, the TP, FN, you just need to
Write the formula only lah.
Yeah, that's formula. I don't give you the specific numbers and then you do the calculation. So no calculation. Yeah.
So no calculation lah.
No calculation, but maybe you still need to write, for example, the formula.
And teacher, can I ask you something? During this exam, we need to memorize all the exercise or not?
The exam question, so we'll talk more about the exam in the last lecture. But the exam is designed to cover as many content as possible.
So we just need to memorize the definition or like something need to memorize a lot, because something that we cannot remember.
Yeah, so regarding the memorization, that's the basic for study. So, but the key is to understand, for example, like this one, as long as you understand the definition of the code, so it's easy to write the formula. So you can also say this is memorization, but for studying, the memorization is necessary for any subject.
So for exam, we will go through about the final exam practices, right?
There's no practice exam.
Oh, okay, thank you.
We'll talk more about that in the practice actually. Don't worry about it. The question will be hard. Okay, so this recall, one question about the recall. So now using recall, you can, so given the previous very simple classifier, so you can know that the recall is 0. So you can easily identify something. But however, if you only look at the accuracy, you may think that the classifier is able to classify. Actually, it's not 0. So it means that the classifier can never catch the positive predictions. And besides recall, another important metric is called precision. So in the same way as recall, so we instead of remembering the formula, the key is that if you understand the definition, you can easily rewrite the formula. So the definition of precision is that you want to calculate the proportion of true positives among data points that have been predicted as positive. So it means that for all the positive predictions, we want to know the proportion of them that are correct. For example, your model say, oh, I have predicted 1,000 sick people, and then we want to know what's the percent of real sick people among all the positive predictions, and that is precision. So here, let's look at the formula. Now you can understand the formula. So given all the positive predictions, so what are they? They are true positive and false positives. So they are all, and the sum of them represents all the positive predictions. And we want to know the proportion of the correct predictions. So that's why we have the true positive divided by the sum of TP and F. So this is the formula of precision. And here we have two examples. So for these two, we have two models, and then we generate the confusion matrix for both of them. And then even the accuracy, they are the same. But however, if you calculate the precision, then you can notice that the model 1 is better in terms of precision. So for example, if a model gives 100 precision, then it means that whenever the model says the data is positive, you can reliably believe that the data is positive. So this is the precision. And then we have three different metrics. So the accuracy, recall, and the precision. But for sometimes people are more interested about the precision and recall, especially for the medical detection. And then, so given a model, and now we have precision and recall. So we have precision and recall. And then given different models, so their values may be different. So for example, for model A, precision may be higher. For model B, the recall may be higher. Now, how can we compare these two models? So how can we get one metric to say, oh, model 1 is better than model 2? And then people debate X. So for X, we want to combine the precision and the recall into a single value. And this way, we can compare different models. So the formula for F score is this one, so it's quite complex. And normally, we only focus on F1 score. So for F1 score, you can see that we just calculate the balance value between precision and recall. So P is precision, R is the recall. And then the higher F score is a bad model. So in this way, instead of using two values to compare different models, and at the end, you have a single value that you can rely on to compare different models. So we have discussed how to evaluate models, and now let's discuss how to set up the data set for training a machine learning model. So in a supervised learning problem, then we are given the label examples of data that we want to classify. So for example, we are given the bank account registrations, logins, emails, etc. And then our goal is to get a model that can predict future data based on the past data. And past data are the training data. And the future data, so the future data, so we can consider them as the testing data sets. And we want to also reserve, so during the training, so at the beginning, so we will collect a lot of data. So for example, we collect like 1 million data. However, we don't want to use all the data to train the model, because we also want some data to behave like the future data, and we want to evaluate the model. So therefore, we need to split the data. So a typical way is that we can split the total data into two sets. So the first one is the training set. So that's if to train your data, you update your data using the training data set. And then we can have the validation data set. And lastly, we have the testing data set. So we're going to talk about those. So the goal is that given all the collected data, so we can randomly split them into three parts. The majority part is the training set. So this data set is used to train the model. For example, when we run gradient descent, we use the training data set. And the second part is the validation set. And also nowadays, if you look at the literature, people also refer it to variable set. And the purpose of the validation set is to evaluate and iterate the model by the learning algorithm. For example, you can use the validation data sets to tune the parameters based on the performance of the validation data sets. But however, nowadays, for some like large data sets, so it's not necessary to have the validation data sets. And after you have already trained the model, and then you keep the model floated, and then you evaluate the model on the testing data sets to estimate the real performance of the model after deployment. So for the testing data sets, it's never touched during training. Okay. And if you notice some like online competitions, for example, on Kaggle, so sometimes they organize the competitions different, and they will keep the testing data set secret. So only after the deadline, they will just evaluate the model on the testing data set. So this can prevent cheating of the training. Okay, and here is the question. So why do we need the validation set? Because we only need the training set to train the model. But why sometimes we need the validation data set? Because for the testing data set, so there's no doubt we don't touch the testing data set during the training. So we don't know the testing data set during the training. And after the model is floated, and then we use the testing data set and to generate the report and that's it. Why do we need the validation data sets sometimes? But this is because when you train a model, so it's very easy for the model to remember the training data set, especially for deep learning. So given, for example, this is a graph for the loss function, so it's very easy that the loss function of the data of the training data set to decrease rapidly to 0. And then you may say, oh, I just keep training, and then until the loss is very small, and then we use the model to test. But this may not be true, because the model may just memorize or just remember the training data set. And then when you use the model at this position, the model may perform very worse in the real world. So therefore, people use a validation data set. So during training, you do not only use the testing data set. At the same time, you also evaluate the cost function on the validation data set. And that what normally you will notice that, so at the beginning, the validation cost or the validation loss will increase together with the training. But however, after some time, when the model is overfit on the training data set, so you can notice that the validation loss will bounce back. So therefore, you want to choose a model that is trained on the training data set, but also behave good on the validation data set, so we can stop the training. So you can use the validation set to guide the training of the model. And then highly likely, so because the training, so the model parameters are not fine-tuned on the validation data set, although we store it here. And highly likely, given a new testing data set, your behavior will be similar to the validation data set. So that can give you a reliable prediction of the model performance in the real world. So imagine that without the validation set, only have the training data set, you don't know when to stop training. So this is especially important for small data sets. So for example, you only have a couple of thousand training data sets. So it's very easy to overfit. But this is not necessary for large data sets. For example, you are using the model to learn image classification on a very large image data set. That image data set contains like 1 million or 10 million of images. Then so that for such large data sets, so it's unnecessary. So it's not easy for the model to overfit. So for large data sets, people directly use the model. So directly train the model on the training data set. So people do not use validation on the large data sets. And for small data sets, so validation set is still very useful. Okay. So notice that during training, we can touch the validation set. But however, during testing, we do not touch the testing set. And another usage for the training set is that we can also use that to fine-tune some learning parameters. For example, like the learning rate. So for example, you choose learning rate 0.001 or 0.002. And both of them can decrease the training loss very quickly. But maybe you can notice that on the validation set, maybe 0.01 is much better. For example, it can reduce the validation set to this one, to some line like this. And if you are using a large one, you can see the validation loss just bounce back. So this is the difference between training, validation, and testing test. So now let's talk about the code framework for this subject. So we will use PyTorch to develop the machine learning, to develop the deep learning algorithms. And a key component in PyTorch is called tensor. So tensors are specialized data structure that are very familiar to arrays and matrix. So for matrix, there are 2D data sets. Also. So for matrix, they are 2D. So for example, given a matrix is 2D. And then for tensors, it's like we have like high-dimensional matrix. So for example, if you want to represent the images using the using tensor, then for a color image, so for example, we have 3 by 32 by 32. 3 is the channels. We have RGB channels. And 32 and 32 are sizes of the image. So therefore, we cannot use a matrix to represent that, because for matrix it's just 3D. But we can stack 3 matrices together. So we have matrix for the R channel, matrix for the G channel, and matrix for the B channel. And then we have 3 matrices together, we stack them on top, and then we get tensor. So you can just simply consider that tensor is just an extension of matrix to higher dimensional space. So that's tensor. Actually, tensor is a physical term, so we don't dive into the very details of the tensor. So you can just simply consider tensor as a high dimensional extension of matrix. And then in PyTorch, we use tensors to encode the inputs and outputs of a model. So the inputs and outputs, they will be stored in tensor. So this is the data structure in PyTorch. And also for the model parameters, they're also stored using the tensor data structure. And for tensors, they can run on GPUs and other hardware accelerators. So in the future, if you graduate and work in Google, so in Google, they encourage people to use their TPU instead of GPU. So that TPU is a hardware developed by Google. So inside Google, you will be encouraged to use TPU. But for tensor, it's okay. It can work on GPU and also on TPU. So you don't need to worry too much about that. You just set up the environments and you don't need to even change your code. And the tensors are similar to the NumPy's ND array. So NumPy is just a module in Python. So NumPy is a library for the Python programming language, especially for support of large calculation. So large calculation of the multi-dimensional array and the matrix. And in NumPy, it provides a lot of high-level mathematical functions to operate on the arrays. For example, if you want to calculate the multiplication between 2 arrays, you don't need to write the for loops. You can use the APIs from NumPy. And the APIs between NumPy and tensor, they are very similar. So basically, if you understand how to use NumPy, you know how to use tensors. If you understand how to use tensors, and then you can understand how to use NumPy. So they are very similar to each other. But the difference is that for NumPy, the data structure only runs on CPU. So here you can see the necessary that we need to use the tensors because we want to use GPU to accelerate the training of the deep learning models. And the APIs are very similar, and even in your Python code, you can really convert them between each other. So for example, you can call torch from NumPy. In this way, you can convert an ND array to a tensor. Or you can convert a tensor to an ND array. For example, given a tensor, you can say dot map. Sometimes you may need to call detach, and you can see the examples in the last. But what you want to know, what you need to know is that you can convert tensors and numpy to each other. And in lab 1, so you will experiment with numpy and the torch. And this subject will use this data set intensively for labs and assignments. And this is a classic one CSIT. This is a simple benchmark data set for image classification. It only consists of 10 different classes. For example, the airplane, automobile, etc., plus one truck. And these 10 classes are here. And this data set only contains small images. 3 by 32 by 32, so 3 means color images. So RGB. So here you know that you can only use tensor to store because we cannot use a single matrix. Matrix is just 2D. And now we have an abstraction, so we need to use tensors to store the images. And this is the data set. And here, so we can go through a simple tutorial to train your classifier. And this tutorial is based on the PyTorch tutorial. So if you do not have AI background, so in your free time, you can invest your time on the official website. So there are a lot of free tutorials of using PyTorch for beginners. And in this simple example, so we will do the following. So we can, first of all, we load the dataset, and then we process the dataset. So normally given the images, we do not directly input the images to the model. We need to normalize the images. So we do the same for the training and the testing. And basically, we don't need to develop the function ourselves. We just call the APIs. For example, we can call the APIs in Torch Vision. And Torch Vision provides a lot of useful functions for computer vision tasks. And now we define a neural network. So this is a convolutional neural network. So if you understand what is convolution, so that's okay. So in this subject, we don't have into details. So basically, you only need to know that people use convolutional neural network for image classification, so that's okay. And we treat this model as a black box model. So you only need to know that given the input is an image, and the output can be the link. So that's the black box model. And then we define the loss function. So for image classification, a typical one is cross-entropy loss. So this loss is also implemented in PyTorch. So you can directly use the API to define this loss function. And then you use a loop to train your neural network. And finally, we test the network on the testing dataset. And because we provide a lot of comments on this code, so we don't go into the code in very detail. So just briefly go through the code. So here we can import the module from the Torch Vision, and then here's the transformation that we want to do for the data. So basically, what we want that we want to conform the data to tensors, and then we want to do the normalization. So for normalization, means that we want to convert the data into zero and unit variables. So that is normalization. And then is the batch size. The batch size is how many images that we want to train the model for each iteration. And then you can use the APIs to load the data set. So CSIT. So this can, using the API, you can even download the data set from the server. So you don't need to handle the downloading of the data. So you can prepare the training and testing. So after you prepare the data set, you can define the model. So in this subject, you will be given the model architecture. So you don't need to define the models by yourself. All the model architectures are given. So if you do not understand the max pool, count 2D, that's not bad, because the architecture will be provided. After giving the architecture, so you need to create the model. So you just call the constructor. And remember that after you create the model, move the model to GP, because you want to use GPU to train the model. So that means straightforward, just say 2 and GPU. So most of the time we use 2. So this is also true when we are using Kaggle. Because on Kaggle, the environment is based on 2. And then we can define our loss function. So loss function is cross-entropy loss. So we don't need to go to the details. Just call the API. The API will create the loss function for you. So right here, cross-entropy loss. And then we create our optimizer. So we want to, the optimizer implements the optimization function. Here we are using Python. Python is a variant of gradient descent. So we don't need to understand the details, we can directly use the other optimizer. So you ask the other to optimize the parameters of the model, set the learning rate. Okay. And then remember that in PyTorch, when you train the model, you set the model into the training mode. So that's training. And after that, you can start the training loop. So that's just a simple loop. For the loop, you get the data from the training set. You get the data and also labels. And remember that in PyTorch, before you do gradient descent, you need to set the gradient to 0. And in that one, you will experiment with the case that if you forget this line of code, what will happen? Because in PyTorch, if you do not zero grade, so if you do not set the gradients to 0, then the gradients will accumulate. That can cause a lot of issues with optimization. Therefore, a standard process in optimization is that you set gradient to 0, you pass the data to the model, you do the backward propagation, and then you optimize. So backward propagation is that you calculate the gradients. Optimize means that you use the gradients to update the parameters. Okay. So you can see that we just use this in sequence. So 0 gradients, the model parameters, and then you pass the inputs to the model. So this way you can get the output. And then you want, given the output and the ground truth labels, you want to calculate the loss. So you can simply use the API to give you the loss. And then given the loss function, you want to calculate gradients because you want to optimize the model. So remember that when we do optimization, we want to go in the opposite direction of the gradients. You don't need to do that yourself because this is already implemented by the optimizer. So you can say optimizer step. So where you a step of the gradient descent. Okay. And after training, you can also save the model weights. And this is actually important when you are doing assignments. So for assignments, maybe you need to train the model at some time. So for assignment 1, you need to generate the text. In assignment 2, you need to train a couple of models. So regardless of generating the text and the training models, so you want to save them into your working space on Kaggle. Because sometimes if you stop the session, and then after you start the session again, if you haven't stored the previous calculated results, then you need to calculate them again. So maybe your 30 hours are not enough to do the training each time when you restart the Kaggle. So therefore, you need to store the results on Kaggle. And in that one, you will learn how to store the results on Kaggle. And after you store the results, and next time you can also read the pre-trained. So you can read the already trained weights and to initialize the model. And then you can evaluate the model. So in PyTorch, when you evaluate the model, remember to set the model in the evaluate mode. Okay. And finally, we can start evaluation. So during evaluation, we don't need to calculate any gradients. So this can speed up the calculation. So normally we set up the context. So with Torch, no gradients. So therefore, inside these which statements, no gradients will be calculated. This can save a lot of calculation. And during evaluation, so we just get data from the testing dataset. So you can see that here we are using the testing loader. So get the data, that's the model to do predictions on the data. So we get the maximum predictions, and then we treat them as labels. So we can check how many images we have correctly recognized. And this way, we can calculate the accuracy. So in your free time, you can go through this this lecture slides, because you can see itself is relevant here. A lot of comments are here. And also in your lab one, you will train your own work on this environment. So basically you will follow the same steps in your lab. So here's the code base provided for this subject. So basically we provide different files. So we have the attacks. So soon we'll discuss the PGP attack and the CW attack and the attack folder. And then we have the autoencoder folder. So this will be used in assignment 2. And later we'll talk about what is autoencode. And it is theoretical control part. And then we will provide 2 classical models. They are classifiers, especially for images. So one is the ResNet, one is BGG. So you don't need to design your own model sample. You are provided with the definition of the models. And also, we have the data set. So for the poison data set, so on Wednesday, we will talk about vector attacks. So you will know what you will mean by poison data set. And also, we provide the subset. The subset is optional, because this will split the training data set into a subset. So this can be useful if you want to only use a subset to accelerate your experiments. That's optional, so you can use it or not. And then for the visualization folder, so we have the backcode. So this is used in the lab, the cyber training. This is used to visualize the gradients. And also we have the model trainer. So this is the core code in the code base. It provides the training management. So basically, it will use so it will load the training data set, load the testing data set, and implement the training. So you can also look at how it is implemented in the model training. And then is the setup. So the setup and the utilities, they provide some useful constants and general functions. So you can also go through these. So in the labs and the assignments, but basically you can base your code on this code base. And also in your assignments, so sometimes you find that you want to modify the code in the code base. And what you can do is that, for example, you want to modify the poisons of QI. So you do not directly modify this file, because when you submit your code, you do not submit the code base. So therefore, even if you modify this one, the tutor cannot see what you have done. So therefore, you can copy the code that you want to modify into your own code, and then you modify the code there, and then you call your own function, or create your own classes. So do not modify the code base, because you don't need to submit the code base for the assignment. So we have just said the model trainer is the core part in the code base. So it's used to train your models. So it provides the model training support and covers all the tasks in the subject. And for your assignments, so you need to know how to use the model trainer. So otherwise, you may need to implement the training yourself. So that's also your. So you're also welcome to develop your own training. So if you prefer, or otherwise you can use the model training to train your model. And here's the setup on Kaggle. So by default, you need to upload the code base to Kaggle. And this can be uploaded to the folder like Kaggle input datasets, and then everyone has a different username. And then normally we name it as UWS30 and code base. So you can change it to other folder names as you like. But if you change it to different one, then you need to also modify the setup code in the provided file. So if you change the name, so you need to also change the first step in the Python notebook file. Besides the code, you can also upload the pre-trained models. So for labs, you are provided with the pre-trained models to save your time. So you can run so in the labs, the code is already developed, so you can train the models from scratch. If you want to save some time, you can download the already trained model, and then save some computation. And for the assignment, you will be provided with the target model. For example, in assignment 1, you will attack the same vehicle model. So in assignment 1, so all of you will be provided with the same vehicle model. And you need to upload the vehicle model to Kafka, so that you can load the model and then attack the model. So you will know how to upload the code base and pre-trained models in Python also. So here's an example. So if you use your own folder names, then you need to change the corresponding name in the notebook file. So for the labs and the assignments, so you'll be provided with the pre-trained models. So for the labs, the pre-trained models are just for saving your computational time, so that you can save your GPU for assignments. But for the assignments, you must use the provided pre-trained models, so that can provide consistent marking for your students, because everyone will attack the same model. So here are the steps to use the pre-trained model. So first of all, download the pre-trained model by the provided link. So the link can be found in the notebook file. And then you can unzip the pre-trained model locally. So this option, you can unzip it or not. Because even if you do not unzip it, you upload the zip file to Kafka. Kafka can unzip it for you. So this option. So, and then you upload the zip file or unzip file to the input folder of Kafka. So you will know how to do it in your lab. And then you specify the directory of the target model. So you can change the directory if you are not using the default names. So more details can be found in Python. And any questions so far about the target? And the assignments are designed as a task-driven development. So it means that after you develop your code, you can actually run your solution and immediately know the marks. So we have discussed at the beginning of this lecture. So even if, for example, even if it shows the marks, but then cannot be the final marks, because your code will be reviewed by the tutor. And the tutor may deduct marks if you violate some assumptions. So therefore, the marks automatically calculated are just the maximum marks that you can potentially achieve for the code part. And the markers, they will manually check your code. And so sometimes if you break the rules, and then will result in 0 marks. The specific rules will be classified in the instructions. That will ensure that you read the instructions carefully. And if you are confused about the instructions, then you can ask the tutor to classify in the labs. So that's why remember to attend the labs, because that's the time that you meet the tutor face-to-face. And some rule-breaking behaviors that were identified in the previous sessions. So here are some examples. For example, so students can violate the assumptions that are clearly specified in the instructions. So, for example, if we do not allow you to calculate gradients using the target model. But however, if the solution uses the gradients, then that will be 0 marks. And also, we have previously identified that some students, they change the marking criteria for achieving marks. And this will result in 0 marks, because we need to make sure that the criteria are original. And that can be fair for every student. So normally, besides your solution, if you change the code in the notebook, normally you only need to change the path to data science models if you are using a different setup. That's the normal place you want to change. So 0 marks will be awarded if the marking criteria are not original. And here are some tips for using Kafka. So you can code offline and then use the GPU when the code is ready. So this can save your GPU time because you only have 30 hours per week. So you use the GPU hours wisely. And if you have a physical GPU, so you are welcome to configure it locally and then run code locally. So you can use VS Code, PyCharm, etc. We can discuss in the beginning of this subject of this lecture. So, however, if you are using other tools, then you configure it by yourself, because officially you only support CAP. And also, if you are using your local environments, you are welcome to change the setup. But however, do not change the marking platform. That is the core to marking to mark the assignment. So when you do the environment, so keep in mind when you need to GPU core.
Also do.
And so before you leave Kaggle, so remember to stop the session. So do not leave the session over the night. Otherwise, 30 hours can be easily consumed. So also save your travel model and best results in the working program. So you are not going to do that in level. This can save you a lot of time. This can reduce the computation when you the notebook. Okay? So you don't need to train the models from scratch.
I hope.
And also, this can make your results repeatable. Because when you submit your assignments, sometimes you actually stop the session. But however, if you forget to save your previous results, you may generate again. And that can give you a different result. So therefore, if you save your results, then you can make your learning repeatable. And in the model trainer document, actually provide the code to save and launch the models. And also in that one, you will see the specific examples. So you can basically use the torch.save API to save the model weights. This can also be used to save general answers in the text. And you can find more about the API in this website. And here are the tips to save in this subject. So first of all, AI is a very practical subject. So therefore, you need to do a lot of practice. And in your free time, so you can explore the PyTorch tutorials. You can find a lot of tutorials for the official website. And also get prepared for the lab tests. So when you start the lab test, then the timer starts. So you cannot stop the timer. So therefore get prepared before you start the lab test. And you can start the test anytime before the deadline and anywhere you like. So yeah, yes.
So for the lab test is like quiz, right?
Yeah, quiz, yeah. The multiple choice questions are
So quiz is in the online quiz, right?
Yeah, online quiz.
Need to do at the lab or anywhere also can.
Yeah, anywhere, anytime before the deadline.
So any got start time or not?
No specific start time. You can do anytime before the deadline.
So only the deadline given, you can start anytime, anywhere, right?
Yeah, you can start
I
anytime.
also can do.
And you can even start if you want.
Or during the lab, because I
Yeah.
saw this during the lab.
Yeah, that's called lab test, but you don't need to do that in the lab.
Don't have to do that now.
Yeah, it's okay. But get prepared. Because when you start, you cannot stop the time. Okay, so anytime, anywhere, just before the deadline. Okay, so during the test, because it's timed, so manage your time wisely. And for the lab test, they are open book. So, but however, you should be aware that the time is not enough to consult the lecture slides for every question. So that's why you need to get prepared for the lab test. And the solutions and the explanations will be available after the deadline. So when you submit your quiz, you cannot see the answers. The answers will be released only after the deadline. So at that time, everyone has finished the quiz. So ask your tutor for help whenever you are confused about the level assignments. And your tutors will mark your assignments. And then if you are not satisfied with your marks, then you can build it with the mark. And then if you are still unsatisfied, then you can email and also CC the mark. And then I will let you with the results and make a final decision. So remember that you contact your tutor first, and then email if you are still unsatisfied. So here's are some situations for different background students. So if you are already familiar with AI and you have strong programming skills, so this subject can be enjoyable. However, if you do not have AI background and your programming is strong, then this subject is slightly changing. So because you need to learn the AI basics and standard training pipeline quickly in this semester. However, if you do not have AI background as your programming is weak, then this subject can be changing. We know that no pen is no gain. So you can find expectation of this subject. And because we still have time, so we'll start the next lecture. So any questions? Okay, so we have just talked about the AI basics. Because we still actually I will start the next lecture. Because next lecture have a lot of content, so it's not enough to cover them just in one lecture. So we just start it. Okay, and here we start the core part of the subject. And now we talk about the attacks. So how to fool a model. And basically, we can fool a model in different ways. And we start with the very basic one, that's called several examples. And this is outline of the subject of this lecture. We will talk about the several machine learning, and then we'll talk about the several examples. For several examples, they are tests. So therefore, we have different assumptions to generate the text. So we can have white box text, black box text, and also we can generate physical text. So besides the digital text, so that can only exist in the digital format, we can also generate physical text, so that can be captured by real-world cameras. And I will talk about the universal result applications, so we'll learn that soon. And also, we finally will talk about the unrestricted text. And machine learning models, they are doing well, simply in the real world. So we can find them everywhere in our life. So we can find the image classification, self-driving cars, object detection, and also the speech tuning tasks. And we think that they are very successful in the real world. And the interesting question is that, are models just collapse? So first of all, what is collapse? And this picture was captured, so you can see that more than 100 years ago, 1904. So very old picture. So Hans is what's the name of this horse? So his name is Hans. And this phenomenon is called collapse. So this was Hans, and he was the trainer of Hans. And the trainer claimed that Hans could do calculation, simple calculation, that 1 plus 2 equals to 3. Hans could do that. But that was very weird, even nowadays, because to the best of human knowledge, horses are not clever enough to do calculations. So therefore, at that time, although the trainer has organized a lot of shows of Hans, but the animal researchers at that time, they were still very suspect. They suspect whether Hans could do calculation. So therefore, they did the research on Hans. And finally, what they found is that Hans did the expression, Hans did the calculation based on some shortcut strategy. So what did Hans do was that, so when the trainer say, oh, let's calculate at 2 plus 2, so you know that's 4. And then Hans will look the ground at 1, 2, 3, 4. And at that time, Hans will notice that the audience actually they separated. So Hans noticed the expression from the audience, and that Hans just stopped the calculation, the slow point calculation. So in this way, the trainer claimed that Hans could do calculation. And then the researchers, they figured out that cats could not do calculation. Cats just grabs the expression from the audience and also the expression from the trainer. So therefore, that was just cheating in calculation. And nowadays, people refer such phenomena as cats for that. And so therefore, the question is that are deep learning models or machine learning models, they are just clever cats. So we can use machine learning models to do classification. So giving it an image of cat, the model can say, oh, this is a cat, or this is a dog, etc. However, as model rarely learn the concept of cat or concept of dog. Just the model is just a cat, and the model is using some strategy to cheat in the real world. So this is the question. And unfortunately, the answer is true. So we are just showing this image at the beginning of this lecture. So given the image of a panda, if we do not do anything, the model say, oh, this is a panda, 57% confidence. And then if we generate some noise and give a noise to the panda, the image is still the same. To us, it's still the same. But now the model say, oh, this is not a image of a panda. It's an image of a gibbon. And even worse, the model say, I'm 99% confident that this is a gibbon. So this is evidence that, at least for this model, when the model is doing image classification, the model is just cheap. So the model is just a clever test to do the image classification. Because we can easily fool the model. We can generate the same, or almost the same image, and then the model say this is a gibbon. That's curious, you can never say this is a gibbon. And this is called the clever test effect in machine learning. So specifically, this happens when models achieve high accuracy by exploring spurious features. So what are spurious features? Spurious features are non-causal backgrounds or correlations in data that machine learning mistakenly used to make predictions. So imagine that, for example, we have a data set of cats and dogs, and we train the model to classify between cats and dogs. But just by chance, all the cats, so all the images of cats are captured in the daytime, and all the images of dogs are captured during the nighttime. Then the model can just simply say, oh, if there's enough light, then it's a cat. If there is not enough light, then it is dog. Yeah, it can generate 100% accuracy. But however, this is just a cheating strategy because the model is using spurious features to do the task. The model does not learn the real task. It just uses the spurious features to make the predictions. And that was the clever test effect in machine learning. And in statistics, a very well-known statement is that correlation does not imply causation. So in this setting, models fail to learn the underlying concepts. The model just cheats by learning the correlation between the data and the labels. So just as the previous example, the model say, well, there's not enough light, then the image is wrong. Yeah, that's true. That can give you the correct prediction, but that's not the real reason of the classification. So this is just similar to the clever hands. So hands that did the calculation by reading human expressions. If you are using Google to search the keywords of adversarial machine learning, so you can find that this topic just gets very hot recently. So it's just 1916. So before 2016. So you can see that almost no one is looking at this keywords. And then almost just within these 10 years, this adversarial machine learning term gets very hot. And this is caused by the clever hands in machine learning. Because when people identify the clever hands effect in machine learning, everyone was very surprised. Because before that, we believed we found intelligent machines. But after that, we found that most of the machines, maybe they are just cheap. Even like ChatGPT. So when you talk to ChatGPT, they give you some response. So you may think, well, ChatGPT are very clever. But later we will learn the hallucinations in large language models. The ChatGPT is also learning some correlations of the data. So therefore, this gives rise to the research topic on adversarial machine learning, and people get very interested in this topic. That's very recent. So, what is the definition of adversarial training? So, in adversarial training, attackers they are aware of the machine learning techniques being deployed against them. And they can, for example, they can contaminate the training data to manipulate a learned classifier. And the purpose of the attack is that they want to evade subsequent classification. Or they can manipulate the specific some metadata, and after which the machine learning algorithms make their decisions. And this way, the attackers they can exploit the weakness in these algorithms. And this is called adversarial machine learning. So to put it simple, that means that the attackers they want to fool the machine learning model. So that's it, adversarial machine learning. And in adversarial machine learning, we have a lot of different topics. So the very beginning one is the adversarial examples, and then we also have backdoor attacks and model stealing, etc. And this is also a very active topic. And let's look at the first attack in this subject. So we have shown that the models they can be fooled by just adding some small noise. And then this attack is so the name of this attack is called adversarial example. So let's look at the definition of adversarial example. So given the original input, so that's the input, for example, an image of a panda. Then what we want is that we want to generate an adversarial example, so x prime. And x prime is enhanced by slightly modifying x. So we want to generate a new panda image by slightly modifying the original panda image. And here's what we can do. So given the panda image, we just add a small noise. So small noise is denoted by delta. And then we get the new panda image. And we want the generated attack. So x prime is similar compared to original panda. And how to measure the similarity between different images? So here's an example. We can measure the L1 node. So here you can see we have a double column, so double vertical bar here, and then we have one, so this is called the L1 node. And now we want the L1 node to be less than a small band. So this way we can make sure that the generated attack is very similar compared to the original clean image. And here we have the definition of the vector node or the LP node. So we have just an example of L1 node, and by definition, we have the vector node. So for vector node, the locations, we have double column here, and then we have a small p, and p denotes which node we are referring to. We have like L1 node, L2 node, etc. And this is also, so this is called p node or LP node. So we can choose values from p equals to 1, 2, 3, etc. until infinity. And the definition of the LP node is that, so LP node equals to the sum of absolute values of each element. And we raise the absolute values to the power of p. And then we raise the sum to the power of 1 over p. So this is the definition. So it was here. For the v here, this is a vector. So that's why we are calling it a vector. And by definition, the infinity node is just the maximum absolute value in the all the elements. So this is the definition of infinity node. And for the when p equals to 1, so this is L1 node. So if we go back to the formula, so you can see that this formula just becomes this formula. Also, this formula, so if we set p equal to 1, so this formula just calculates the sum of absolute values. So So the one here disappears, and we raise to the power one, the p disappears, so we just calculate the sum of absolute values. So that's L1 mole. And what is L2 mole? So we set p equal to q. That is just a Euclidean distance. So that's it. Because here, when we calculate the LP mole, most of the time, we calculate the LP mole with respect to the difference between the attack and the original image. So here, after we generate the attack, we calculate the difference between them, and then we want to construct the difference within the L1 or L2 mole. So that's why when p equals to q is equivalent to the Euclidean distance. So we just calculate the Euclidean distance. So we calculate the square root of the sum of squares. So for example, we have like v0 squared plus v1 squared plus v2 squared. So just actually calculate the Euclidean, or just calculate Euclidean distance. Okay. And in your assignment 1, so you are generating a text. And how do you make sure that your attacks are resembling the original input? Then in the criteria, you will calculate the L1 mole between your attacks and the original image. And then we will use the code to make sure that the L1 mole of your generated attack is within the specified band. So for example, given the L1 mole, you want to make sure that your generated attack in terms of L1 mole, for example, is less than 0.04 example. So this will be your value. So any questions about the definition of solid cells? Any questions? So when you understand the solid examples, the key is that you can go back to the panda example. So you want to modify the panda. So you want to generate some noise to add to the panda, and then generate the result. So that's the attack that you want to generate. But however, you want your attack still look similar to the clean panda image. Therefore, you want to calculate the difference. So you want to make sure that the difference between your attack and the original panda is very small. But how to measure this difference? So therefore, first of all, you can calculate the difference. So here you can see that you calculate the difference, and then you can measure the LP mole. So specifically, you can calculate the L1 mole, L2 mole, or L infinity. So you can make the choice yourself. And then you want to make sure that the LP mole is smaller than the specified value. And this way, you can make sure that the generated attack still look like the original clean image. So that's the L1. And then for the attacks. So we are just talking about the definition of solid examples. And then when we generate attacks, we can generate targeted attacks, and also we can generate anti-targeted attacks. So for targeted attacks, we want to fool a model to output predefined labels. So it means that you already have our labels in our part. So for example, we want the model to predict a panda symbol. Therefore, we generate some noise to put on the panda image, and the model will say this is a ball. And this is the success of a targeted attack. And for an targeted attack, the goal is that we just want to fool a model to output incorrect labels. So we don't care about the final output, but as long as the output is different compared to panda, that means we succeed. So this is the targeted attack. So before we continue, any question about the definition of solid? Yeah, this is the definition. Maybe tonight you can, or maybe you have dinner, you can recall, so you can also have a look at the definition. Actually, definition consists of two parts. The first is that the attack is similar to the input, because so visually you don't want to give a big difference. And then the second part is that how to measure the difference. So you can use the LP to measure the difference. So that's the solid example. So let's talk about the very first attack algorithm. And this was the beginning of the serial machine learning. And after this algorithm was proposed, and people was worried about that the machine learning models, they are just clever hands. And this algorithm is called fast gradient sign method. So given the name, so fast means that this algorithm is very fast to calculate. Gradient means that this algorithm uses gradient information to do the attack. And that sign method, so we'll know that. So we'll soon show that why we have the sign here. Okay. And this algorithm is the white box attack. So for white box attack, it means that the attacker knows everything about the attacker model. And this includes the model architecture, model weights, training data, etc. Just the model, just the attacker knows everything. And it means that the attacker can calculate gradients with respect to the input data. So here is the key. Because the attacker knows everything, including the model weights, then nothing stops the attacker to calculate the input data. And the gradients are very useful to generate the attacks. And here we name the attacks as some examples. And here you can see the difference. When we train the model, we calculate the gradients with respect to the model parameters. And then when we generate the text, we calculate the gradients with respect to the inputs instead of the gradients. Because, for example, given the image of a panda, then we want to modify the panda image instead of modifying the model parameters. So that's why now we calculate the gradients with respect to the inputs. So this is the key to generate the text. And interestingly, there was a story when this method was developed. When the authors, when they developed, that was when they tried to develop a generative model. So for example, given an image of a panda, then they want the model to modify the panda to a dog. So that was the early stage of generative models. And then they try to just modify the image along the direction of gradients. So that's the model to classify the score. But then they find that if we just modify the image a little, the model will say, oh, this is a dog. Although visually, this is still a panda. And then they realize, oh, this actually is a security issue in machine learning. And this gives rise to the fast gradient sign method. So fast gradient sign methods fools a model by calculating gradients only once. And this is very fast. So you just calculate gradients once, and this is simple but very effective. So the algorithm can be implemented just in 3 lines of code. So here we just mathematically represent it. So the first one, that's the J delta xy be the cost function. So this can be the cost entropy. So for image classification, and theta here are the model parameters. So it means that to calculate the cost, we need the dependence on the model parameters, the inputs, and the label. So we have the cost function, and this is used to train the model. For example, an image classifier. Okay, now let's generate the attack. So in the first line of the code, we calculate gradient with respect to the input. The input is an image of a panda. So we calculate the gradients, but not with respect to the model parameters. Now, we calculate the gradients with respect to the input image itself. And then we call the sign method. So we calculate the sign of gradients. So if the gradients is a positive value, the sign becomes 1. If this is a negative value, the sign becomes negative. So this is the sign function. And now we get the sign of gradients. But the sign of gradients can be too large as noise, because we don't want to modify the input panda too much. We just want to generate small noise. So therefore, we multiply it by small value, epsilon. So epsilon is just a small value for your start ability. And next is the key step. So when we do that, we can add the previously calculated noise to the input. And that's it for the attack. So remember that this noise actually represents the direction of gradient. And then if we modify the data along the direction of gradient, remember that we just talked about that at 1 hour ago. If we modify the model parameters, here we not modify the model parameters, we are modifying the input, but the effect is the same. So for the loss function, it does not only depend on the parameters, it also depends on the input. So when we modify the inputs along the direction of gradients, actually we have the same effect. We are increasing the loss function. So we are, because the direction of gradients points to the largest increase for the cost function. So therefore, given the input panda, we modify it. So just consider panda, we store panda in vectors. If we modify the image of panda along the direction of gradients, and we get the new panda image, the new panda image will greatly increase the loss. And then remember that what is the loss function? Loss function measures the error made by the model. So this means that after we modify the input panda and we get the modified panda, we greatly increase the error made by the model. So therefore, the model will make incorrect predictions. And this is the idea that we can fool the model. Because given the original panda image, the model can correctly recognize it. However, we modify the panda image along the direction of gradients. This increases the error. The error is measured by the cost function. We increase the error, and then the model will make incorrect predictions. So in this setting, y is the ground truth label. So here you can see that here we use the plus sign for untargeted attack. If y is the ground truth label. So y is the panda. So we calculate the loss. So here we calculate the loss when the input is panda and also the label is also panda. Then given the panda image, we want to calculate the error that the model predicts as a panda. So if the model correctly recognizes it as a panda, actually the error is very small. However, we modify the panda along the direction of the gradient. Then the loss function or the error will be big. Then the model will make incorrect predictions on the attack. Here. So this is for an target attack, provided y is the label of attack. Okay. And next, this is also can be modified as target attack. However, for target attack, remember that we have predefined label. So we want the model to predict the panda as a dog. So we have a predefined label. So in this setting, y is not the ground truth label. So y is the dog beside the panda. So for untargeted attacks, we don't care about the final output. As long as the output is not panda, then we succeed. But for targeted attack, we want to make sure that the model predicts our desired label. So now y is dog. Then let's look at, and at this setting, the plus sign will be minus sign. So we use minus sign. So let's see why this is the case. Okay. So now y is the dog, the label dog. Then what does this cost function is measured? It measures the error that the prediction, so given the panda image, the error that the model is predicting the panda as a dog. However, we know that at the beginning, the model will correctly recognize this panda. So therefore, if we measure how large that error it is made, if we force the y to be a dog. So given the image of a panda, the model says this is a panda, then mathematically, if we calculate the error, that's if the model predicts as a dog, and this error will be very large. Because regarding the label dog, the model is doing the incorrect prediction. But then, although we want so at the end, we want the model to predict panda as dog. But however, the model said this panda is not dog. So therefore, when we calculate the loss function, this means that the model is making a big error on this. Okay, and now here is the initiating. Okay. So at the beginning, we know that the model is making a big error. So from the perspective of attacking, the model is making a big error. Then we want the model to make small error. So we want the model to make smaller and smaller errors such that the model say, oh, the image of panda is actually making. So this is what we want. So that's why we have, so in the first line, we also calculate the direction of gradients. But however, we want to decrease the cost when we consider y slope. So therefore, we modify the inputs along the opposite direction of gradient. So in this way, we decrease the cost. So remember that we repeat this step again and again, just like when we train the model. Then the model will eventually make a very small error to say, oh, this is a ball. And then actually we fool the model to say this is a ball. So that's why if we are doing tactical attack, then y is the tactical aim. So y is not the conscious aim. And the last line is to constrain the images in the range 0 and 1. Because in PyTorch, if we represent pixels, we use float values for the values in the range 0 and 1. So just click in the edit range. And this is the algorithm of fast gradient sign method. So any questions before this one? So any question about this algorithm? So well, why is the branch stable and then we pair it with plus sign? Because we are doing a tactical test. Just want the model to make errors. For tactical tests, and however we need to change the plus to minus sign. And y is the tactical layer. For example, y is the goal. So the key to understand that is we need to understand what is the definition of loss. So loss is the error that we measure if we, so given the model prediction and our desired prediction. So what is the error made by model? So for tactical attacks, so given the image of a panda, the model says a panda. So although this is true for the model behavior, but however, from the perspective of attacks, this is we can, for the perspective of attacks, we want the model to say this is a door. So from this perspective, actually the model is making a big error. Because the model is not predicting this is a door. The model still says this is a panda. So that's why if we change y to door, and at the beginning, the model will give a very large cost or very large error. And also we want to lower the error. So we want to make the error smaller, such that the model can correctly say, well, this is a door, instead of saying this is a pen. And that's why we want to move to the opposite direction of the gradient. Just like we are optimizing the model parameters. And this is fast gradient sign method for a tactical attack and also tactical attack. I just hope here we'll continue tomorrow. Right, see, any questions before we go? So see you tomorrow.
我記得有咁樣嘅。